Welcome, and thank you for joining us. My name is Dean Lee, and I am Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the great pleasure of presenting a public lecture by Professor Kate Scholberg entitled How to See a Star Explode from Underground. Professor Scholberg is Arts and Sciences Distinguished Professor of Physics and Bass Fellow at Duke University. Her broad research interests include experimental elementary particle physics, nuclear physics, astrophysics, and cosmology. Her specific interests in neutrino physics lie at the intersection of these areas. She is a member of the Super Kamiokande, Tokai to Kamioka, and Deep Underground Neutrino experimental collaborations. She is the spokesman of the Coherent experiment, a neutrino scattering experiment located at Oak Ridge National Laboratory, and a co-founder of the Supernova Early Warning System, a global network of neutrino observatories. Professor Scholberg received a bachelor's degree in physics from McGill University and a PhD in physics from the California Institute of Technology. Prior to joining Duke University in 2004, she was a research associate at Boston University and an assistant professor at the Massachusetts Institute of Technology. She is the recipient of a National Science Foundation Faculty Early Career Development Program Award and a Department of Energy Outstanding Junior Investigator Award. She is a Fellow of the American Physical Society and was elected to the National Academy of Sciences in 2022. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. Now, at this time, it is my great pleasure to introduce Professor Scholberg.
Thank you very much. Thanks for that invitation. It's a great pleasure to give this talk. So I'm going to tell you how you can see a star explode from a deep underground location. And the secret for doing this is to use neutrinos. And so neutrinos are what have been often called ghostly particles for good reason, which is that they are a kind of elementary particle that will just go right through things. And the reason we are interested in neutrinos, we have many reasons to be interested in them, but one of the reasons is really just understanding the fundamentals of particle physics. And I'm a particle physicist. And as I guess Dean mentioned, I'm also interested in the intersection between areas where we're interested in very, very large things and very, very small things. And what particle physics is really interested in is what are the fundamental particles that make up the universe? How do they interact with each other? What are the fundamental interactions? And also, how does this fit into the big picture of how the universe came to be? And so that involves studying things on both the very largest and the smallest scales. And about neutrinos are among the fundamental particles of the standard model. And here is a particularly delicious representation of the standard model indicating the fundamental particles. So we have particles that are kind of the ones that make up everyday matter. There's quarks, which make up protons and neutrons, which make up the nuclei of atoms. And then we have leptons. And the most ordinary everyday lepton is the electron, which is also part of an atom. So those are part of the fundamental particles. But there are also many other particles that are more exotic, and these are studied, for example, at colliders, where we're probably heard of the Higgs boson and so on, and really understanding the in depth the interactions of these particles is the business of particle physics. And neutrinos are some of the picture, and they are down here in the lower left in the cupcakes. They are, there is a neutrino for every kind of lepton. So their electrons are the ordinary everyday leptons. Muons are kind of heavier kinds of electrons, and taus are really heavy kinds of electrons. And for each of these fundamental leptons, which have charge, there's a neutrino, which doesn't have any charge, and they are also extremely light. And they are very weird particles. They are very different from other particles and very different from their partner leptons. And one of the really big differences is that they are extremely light. They have less than a 500,000th of the mass of an electron. And so if a electron's an elephant size, a neutrino may be smaller than a mouse, and that is weird. Nobody really quite understands why that's so. They also interact hardly at all with matter. And if you know what about the forces of nature that we understand in the standard model, we know that there are 3 forces and then also gravity. And the forces are the strong force, which is what is involved in the particles inside nuclei. There's electromagnetism, which is the everyday force that governs most interactions that you deal with in your everyday life. There's the weak interaction, and that is really the only kind of force or interaction that neutrinos feel. There's also gravity. We know that because neutrinos have mass, they have some tiny mass, they do feel some gravity. But how gravity fits in with the others is another big question. But because neutrinos really interact only weakly, they don't have strong or electromagnetic forces, they are kind of weird. And just to indicate how weakly neutrinos interact with matter, just to give you an example here, different kinds of particles interact more or less with matter. And if you take, for example, an alpha particle, that's a kind of radiation, it's a helium nucleus that will basically not get through much matter at all. You can get rid of alpha particles with just a sheet of paper. Beta particles are electrons, and they will go through more than alpha particles, but they can still be stopped by small amounts of matter. Gamma rays are famously penetrating, and they can get much farther. They can get through some reasonable amount of carbon or even lead. However, even compared to gamma rays, neutrinos are much, much more penetrating. And so a neutrino, if you take a neutrino of a similar energy to these particles that can't get through, get through different amounts of matter, a neutrino of similar energy to a gamma ray that can get through 20 centimeters of carbon, a big chunk of graphite, a neutrino of similar energy would go through a light year of carbon before even having a single interaction. They basically go right through things. They interact only very, very rarely and very, very weakly. And here's another kind of illustration of that, is that a neutrino could easily travel through 100,000 Earths before it interacts at all, on average. And so this is extremely, that's the meaning of an extremely weakly interacting particle. So I see there's a question. So yeah, if I spot these questions, I will answer them. Here's a question. Since there's neutrino oscillations, I started to wonder whether the electron, muon, and tau particle might also oscillate. Okay, that's a really great question. And the answer is that because of energy conservation, the masses of electrons, muons, and taus. I didn't really talk about neutrino oscillations, but this is actually how we know that neutrinos have mass. This is an entire side story. But because the difference in mass between different kinds of electrons is very tiny, and so that allows them to quantum mechanically switch between flavors, basically because of the uncertainty principle, that there's enough slop in the actual energies that it allows the particles to effectively change from one state to another. For electrons, muons, and taus, that's actually forbidden. And so the other question about heavier particles is, that's an excellent question. It's an experimental question. And as far as we know, there are not. There's reasons to believe there are not. There could, in fact, in principle, be heavy neutrinos that don't have normal weak interactions, but that's an entire question that is not really known. So I hope you can come back to that if that doesn't fully answer the question. How can we sure they truly exist and aren't just a side effect of other particle interactions if they're so ghostly? We actually have very good evidence that they do exist, because we see we can actually see explicitly their interactions, and actually, again, this is kind of a side story. We can see our signals in our detectors of interactions where you actually, a neutrino will will create particles. And I'm actually going to come to that. So maybe I will I will actually address that in another slide coming up. Okay, so neutrinos mostly just go through you. There's neutrinos, enormous numbers of neutrinos, for example, from the sun coming through you. And how do you actually see them? So I think this is getting at one of the questions. So this probably dates me, but this is a character from Star Trek The Next Generation called Geordi LaForge, and he had this special visor, and this visor allowed him to see neutrinos. And I've always been super jealous of that visor. That would be really great. In fact, it doesn't work. In fact, we have to work very hard to see neutrinos. The way we can actually see them, even though they interact only occasionally, they do interact occasionally. And when they do interact with matter, they create regular charged particles that we can measure in the normal way. We can actually detect these particles. And so the occasional interactions, neutrino comes in, smashes into some matter, and it creates a charged particle that comes out. But because the interactions are so rare, that means that the detectors that we need to build in order to see neutrinos have to be typically very large. And just as an example, some of the existing detectors that we have are at least kiloton scale, so thousands of tons, just enormous detectors. It can be up to tens of kilotons, and even now, kind of approaching the megaton scale. So what it means if the interaction is very rare is that if you want to stop a neutrino, you have to build a detector that has a lot of matter that has a greater probability of stopping a neutrino and observing a really rare interaction. And also, related to the fact that the interactions are very rare, on the surface of the Earth, there's a lot of particles going through you all the time, coming from the sky. If you put your hand out facing the sky, you've got about one cosmic ray muon every second going through your hand. It's basically particles coming from the sky all the time. Of course, you don't feel them, but if you have a detector that's sensitive to neutrinos, you will see signals coming from neutrinos coming from particles from the sky, just cosmic rays all the time. And it's like this constant rain of stuff coming from the sky that is going to light up your detector all the time, with signals that will completely swamp the neutrinos, because the neutrino interactions are very rare. And so if you want to see neutrinos, you have to build a detector that is not only very big, but that has some protection from cosmic rays. You have to be shielded. Particles from the sky will tend to die when they hit the Earth. They will be absorbed by the matter overburden. And so you want to be deep underground if you want to get away from the cosmic rays that will completely swamp your rare neutrino signal. So just as an example, a detector here, this one on the left here, is Super Kamiokande. This is about 40 kilotons of water, and we see only about 8 neutrinos from maybe 10 neutrinos from the sun per day, or a few tens of neutrinos from the sun every day in this enormous detector. But we have 3 cosmic rays per second, even underground, going through the detector. So it's a challenging task to see these really rare signals underground. Okay, so now let me talk about things that explode. So supernovae are stellar explosions. They are basically stars that blow up. And a supernova is defined as a giant burst that results in a star getting basically blown up to smithereens. And for a while, these can be extremely bright. And in the photons that come out, just the light, the electromagnetic radiation that comes from a supernova, for a while, a supernova can be as bright as a galaxy. And I have to qualify that because once a famous astronomer took me to task for saying that, because a regular galaxy is actually brighter than a supernova, but a smallish galaxy will not be brighter than a supernova. But anyway, these things are really extremely bright for a short period of time in photons, in light. So they are really intensely luminous in photons for a short period of time. There's different kinds of supernovae. And I saw this tweet, which I thought was pretty funny, that says that if astronomers were in charge of naming them, pies would be called type 2 cakes. Astronomers like to call things in different types. And there are 2 main types of supernovae. There are type 1a supernovae, and then there are type B2 supernovae. And there's subtypes, but the big major types actually correspond to different kinds of physical events. So type 1a supernovae are actually natural thermonuclear explosions. They're usually related to binary stars that are matter is getting dumped on a star from a companion, and when the thing reaches a critical mass, it just blows up. So this is like a giant thermonuclear explosion. And these are actually very important to astronomy, but they don't emit a lot of neutrinos. The type that I'm interested in, especially, is type 2, which has a different physical mechanism. And this mechanism is that when you have a really massive star that comes to the end of its life and has burned out its nuclear fuel, stars are producing energy by nuclear reactions. And when it runs out of nuclear fuel, usually involves the weak interaction, but lots of energy being pumped out from nuclear reactions. And when the nuclear fuel is exhausted, the star can no longer hold itself up. It's basically a star is held up against the force of its own gravity by the energy that it's producing, by the thermal energy that it's producing. And when it doesn't have any more, not producing any more energy, it will then collapse in on itself. And the result of this collapse is what's called a compact remnant. So it's something that is extremely dense. And so this type 2 model is you basically have a star at the end of its life, it collapses, it scrunches down into a really dense kind of matter. In fact, it is so dense that protons and electrons are squeezed together to make neutrons, and that creates neutrinos. And these kinds of events, these collapses, are enormous producers of neutrinos. For every neutron that gets produced from a proton and electron getting squeezed together, there are neutrinos, but there's also neutrinos that just come from the hot processes that are happening. And so it's basically enormous flash of neutrinos. And the result is this compact remnant. And there are different kinds of compact remnants. And one kind is a neutron star. This is when the neutrons are basically forming their own kind of very dense matter. And this is a visualization of the size of a neutron star. It's basically all of the mass of an entire star, which is packed into an object which is several kilometers scale. And it's, of course, this is not a photograph, but it gives you a sense of the size of this entire, imagine all of the mass of the sun in an object of the size of a city. So these are very exotic objects. And that can be the outcome of a stellar collapse. You get a supernova, and then what's left over is a neutron star. Another possible thing that could happen, and maybe this is kind of more exotic and exciting, and it happens, we know that it happens some of the time. We don't know exactly what fraction of the time it happens, but what can happen is if there's enough matter accreted, you can have a subsequent collapse that the neutrons can't even hold themselves up against their own gravity, and you get collapse to a black hole, which is something that is so dense that not even light can escape. And of course, I think everybody's heard of black holes. They're extremely interesting and exotic objects. And in this case, if this happens following a core collapse, there might actually not be a very bright supernova. So, and this is it's not exactly understood what happens all of the time. Some of the time you may get a neutron star and a really bright supernova, but some of the time you may get only a black hole and not a very bright supernova. What it may look like from an astronomical observation point of view is that you might have a star that just winks out. The star just disappears. And the thing that is really interesting about the neutrinos that come out is that in that case, if a black hole is formed and there's no supernova, you would still see a very bright burst of neutrinos. So this could be, the neutrino burst could be the signature of a black hole formation that might not have a very bright supernova associated with it. And so that would be a really exciting thing, to be able to see this bright burst of neutrinos and maybe no supernova corresponding, or maybe astronomers could even find a star that suddenly disappeared. That would be really, really exciting. Let's see, a non-supernova. Of course, a supernova is also very exciting. There's a lot of very, very interesting things to see about that really, really bright kind of burst. The thing that my research is interested in is this actual burst of neutrinos and how we can detect them. So you get this really brilliant burst of neutrinos over about 10 seconds, or maybe several tens of seconds, and neutrino detectors worldwide are able to see this burst. And the thing about using neutrinos for astronomy is it's kind of both a blessing and a curse. And so this image here is one that I got from a Google search of ghosts escaping. And so it's basically ghosts coming out of something deep inside. And so the exciting thing about neutrinos, the thing that's the blessing, is that if you're studying neutrinos from some astronomical event, astrophysical event, is the neutrinos can tell you what's happening very deep inside really exotic dense objects. And it's regions where the photons will never get out. So the example here would be the early stages of a black hole formation. You're not going to see, the matter overlying is going to be very dense. You're not going to see very much, but the neutrinos are going to get out. You're going to actually see the formation of that black hole. What you would actually see is a very bright burst of neutrinos that suddenly would cut off. And the cutoff would correspond to the formation of the black hole. And even just for a supernova that creates a neutron star, you can also see what's going on very deep inside the protoneutron star, inside at the very late stages of the collapse. And that is inside this really exotic, very, very dense object where it would take the photons a really long time to get out of that object. And so that's really the advantage, is you can kind of X-ray what's going on with these neutrinos that are coming out from very deep inside. But the flip side of that, the curse part, is that because of the weak interactions of neutrinos, you have to really have huge detectors. You really have to make heroic efforts to see any of them at all. So it's kind of a, pros and cons there. So now I want to give kind of a physical explanation for why is it that all of this energy comes out in the form of neutrinos? What is the physical reason for this? And so here's kind of a physical explanation. So if something falls, gravitational potential energy turns into kinetic energy. So a piano falls out of a window, its gravitational potential energy turns into velocity by the time it hits the ground. And then when it hits the ground, it makes a big smash, and that energy turns into sound, it turns into heat. Energy is always conserved, but that energy has to go somewhere when an object falls. The gravitational energy turns into some other kind of energy. Now, when a star falls, that gravitational energy also has to be conserved. It has to go somewhere. And because that energy can leave the star, it can leave this really dense object because neutrinos interact so weakly. Thanks to that weak interaction, all of that energy can leak out of the star very quickly. And so you get this very fast leakage of energy out of the star via neutrinos, and other energy is trapped inside. And it ends up that something like 99% of this gravitational potential energy from a star falling to a star-sized thing into a city-sized thing, that's an enormous fall of material inward, that energy, almost all of it goes into neutrinos. And just to give you a sense of how much energy that is, it's enormous energy. Remember, the electromagnetic part of it actually is, which is as bright as a galaxy, is actually only something like 10 to the minus 4 of the total energy. And so the luminosity in photons is almost the luminosity of an entire galaxy, but that's still only a tiny fraction of the total amount of energy that goes into neutrinos. So enormous amount of energy goes out over a few tenths of seconds in the form of neutrinos. And how this entire explosion actually works is an entire subfield of astrophysics, and there's many researchers who work on the actual computational modeling of how the explosion happens, how the energy gets coupled. Some of it gets coupled to photons and kinetic energy, and how does that actually happen in detail is a topic of numerical study. People run simulations on supernovae on supercomputers. And these are some really nice visualizations. Actually, there's even more up-to-date ones. And the details of this is not completely understood. More recently, people actually do have their simulations really showing that the explosions are happening, but there's still, still a lot of work that needs to be done. And what is clear is that the neutrinos actually are quite intimately involved in the process. They actually interact themselves with the explosion. And that means that we can learn about what's happening deep inside the explosion from looking at the neutrinos. So I see another question. Are neutrinos affected less by gravity compared to photons, and can they escape a collapse into a black hole? So they are affected by gravity, actually in a very similar, they are moving almost very tiny energies, so they're relativistic, but they are affected by gravity. Well, photons are also affected by gravity and general relativity. Can they escape the collapse? They cannot escape the black hole once they're inside the event horizon, but some of them do escape the supernova before the black hole. And so that's what the signature to collapse to a black hole essentially is that you get this really bright burst of neutrinos, and then bam, it just goes to nothing as the black hole is formed. And that's something that would be really, really cool to actually see. And you couldn't see the photons coming from the same, the actual core, because the photons have to come out of the envelope, and that they interact with the envelope a lot. And so it takes them a long time to get out. And so you can't get astronomical information. Observers can't see that black hole formation happening in real time the way that we could see it with neutrinos. And another question I see, neutrinos will not interact with anything else. That means the energy is lost. Well, it's lost to the star, and it is, but it's going out into the universe, and and we are able to capture some of that energy when we capture some tiny fraction of those neutrinos that come out. I think, I guess all of these things are entropy generating. So the energy isn't lost to the universe, but it is, in principle, the neutrinos are, streaming off out there forever. And so it's hard to, the actual fraction of it that we can actually see as an interaction will be very small. Okay, so I hope that answered those questions. So let me go on here. So I just want to mention there has been one example in history of a supernova that was observed both as a supernova and also in neutrinos. And this was a famous supernova 1987A, that happened in the Large Magellanic Cloud, which is actually a small galaxy that is outside of our galaxy. The center of our galaxy is about 10 kiloparsecs away, and so it's about 5 times farther than that. And at that time, there were actually 2 neutrino detectors running, and they were able to observe that burst of neutrinos. And so that is a really, that was a giant thing at the time. But we have not had any nearby supernovae happen since then. We have only those 24 neutrino interactions captured in 1987, and we have not seen that again, although we expect to capture many, many more neutrinos when the next supernova happens. And you can ask, how often do supernovae happen, core collapse supernovae happen in our nearby galactic neighborhood? And the answer is probably a 2 or 3 times a century. So it doesn't happen very often. Here's a very nice visualization of our local area in the universe. So here's the Milky Way, which is where we live. Over here is Andromeda, which is the nearest big galaxy. It's about 700 kiloparsecs away. And you can see here, there's also some little galaxies nearby, including the Large Magellanic Cloud and the Small Magellanic Cloud. And this one is where the 87A supernova happened. And inside this radius is about where you would expect one core collapse about every 30 years. And it's probably about the same number in Andromeda. But we're really only sensitive with neutrinos in a relatively small region around our Milky Way, something like 100 kiloparsecs or so. Although we might get a little bit from Andromeda if a supernova happened there. So why do we want to see these neutrinos? It's a huge list, and I'm just listing a few things. What can we learn? We can learn an enormous number of things. We can learn how the core collapse actually happens. We can see what's happening in the inner core of the supernova from the explosion by looking at the neutrinos that come out from the energies that come out and over the time structure, and actually what the different flavors are. Neutrinos come in these 3 flavors: electron, neutron, and tau, and antineutrinos. We can see how the neutron star might cool. We can see if a black hole forms. That would be huge. We can also learn about the actual, perhaps there could be exotic kinds of remnants. There are things called strange stars that might give particular neutrino signals. And we can also potentially learn about how the star forms heavy elements. We can also learn about neutrino physics. And I'm actually a neutrino physicist, and one of the things I'm very excited about the prospects of seeing neutrinos from a supernova is that we can actually learn about the properties of neutrinos themselves. We can learn about how they change their flavor and how they're and something about their masses. And we can actually also look for new physics that's beyond the standard model. So there's a very, very long list of things that I could spend many talks talking about. And we have a kind of virtuous circle in that the more we learn about, the more we know about the core collapse, about the supernova, actually gravitational waves are also very useful and are actually also prompt and can see inside what's going on inside you get information from deep inside, also from gravitational waves. If we can make a multi-messenger observation in photons and gravitational waves, we can learn more. We're able to extract more neutrino physics. And conversely, if we have neutrino terrestrial experiments, if we learn more about the neutrinos, we end up with a better handle on our models to get information about the core collapse. And so it's really all of the information comes to the party. And if we actually get one of these core collapse supernovae nearby that we can observe in different ways, it will be just tremendous. It will be amazing information. And one thing I just want to point out is that with neutrinos, we see the neutrinos come out promptly. They come out within 10 seconds of the core collapse. And that means we actually have a chance to tell astronomers to go look for something. That the photons may not come out for hours because they have to have a shock wave that comes out of the envelope and then makes an actual observed signal for astronomers. It may be a delay. It could be half an hour. It could even be a day if it's a really thick envelope. And what that means is that if we see the neutrinos right away, we can tell astronomers, oh my God, you better go look for something. And actually, preferably, we'd like to tell them where to look. And we can do that at some level. But even just knowing that something is about to happen would be really exciting and help with the possibility of getting an early observation. I see another question. So the neutrinos will not interact with anything else. That means, I think that was a new question. Is the neutrino detection system large enough and is the supernova neutrino flux large enough that the MSW effect can be used to see where in the sky neutrino sky telescopes might look to find the supernova? Okay, that's a really interesting question. MSW effect, that's got a long, complicated answer, but the MSW effect in the supernova is something that will likely imprint itself on the signal. There's actually also complications to that because the neutrino density inside the supernova is so dense that you actually get neutrino-neutrino interactions, which is a mind-blowing concept because neutrinos are so weakly interacting. The idea they can interact with themselves is amazing. And that can also modify the signal. So there are certainly modifications that come from effects with matter, sort of complicated effects with matter and neutrinos themselves. There's also a matter effect in the Earth, and actually that is a great question because in fact I wrote a paper on that probably about 10 years ago. That in fact you can use the spectrum. In principle, you can use the spectrum of oscillations to tell you how far the neutrinos traveled in Earth matter, which gives you sky location information. And that is probably quite hard to do in practice because you need detectors that are bigger and better energy resolution than we're likely to have in the near term. But that is in fact a concept that works in principle. So yeah, thanks for that question. Okay, so let me talk about how we detect them. So these are four main kinds of neutrino detectors that we have currently in the world. There are detectors that are made of water. It can be either liquid water or solid water. There's detectors that are made of hydrocarbons, which is basically oil-like kind of detectors where it's a material that emits light. It makes a flash of light when particles leave energy in them. These are called scintillator detectors. There are detectors that are made of liquid argon, and these, I'll say a bit more about those. And then there's one example of a detector that's made of lead, where what you're looking for is neutrons that come out when neutrinos interact with it. And there's some others as well. This isn't comprehensive, but these are the main types. Now, most of these detectors are actually not built to look only for supernova neutrinos. So they all pretty much have day jobs. They all have other neutrino physics, which tends to be the primary thing that they're doing. So for example, they're looking for neutrinos that come from the sun, from the atmosphere, or from actually artificial beams of neutrinos that we are sending to these detectors in order to understand actually the flavor oscillation properties of neutrinos. So they typically they're doing some other business in neutrino physics, but as a fantastic side gig, they are able to also see if we happen to have a supernova. Many of these detectors would observe these bursts of neutrinos also extremely well. And in fact, that was the case for the detectors that saw the 1987 A burst. Those were 2 water detectors, and they were actually originally looking for proton decay, and then they were also looking at solar and atmospheric neutrinos, so natural neutrinos that are kind of steady state sources. And then they happened to be online when this burst of neutrinos came in 1987. So a lot of these detectors are also doing other things. So let me just briefly go through different kinds of neutrino detectors. So the water detectors, here the idea is that you have a giant volume of water that is surrounded by photosensors. And what they're looking for is the light, Cherenkov light, that you get when a charged particle is going faster than the speed of light in the material. Now, nothing goes faster than the speed of light in a vacuum, but in material, light is slowed down by the index of refraction. And so it's possible for a charged particle to be going faster than the slowed down speed of light in the material. And when that happens, you get something that's kind of like a sonic boom. It's if you have something going faster than the speed of sound in air, you get a shock wave. This is a picture of a fighter jet with a sonic boom visualized. It's kind of the same thing for a charged particle going faster than the speed of light in water or some other material. You get this kind of sonic boom, except it's a boom of light, and it is in the form of a cone, and looks like a ring when it's projected on the side of a vessel. And so here's just a little more information on that. So you have a shock wave of sound. In this case, it's kind of like a shock wave of light. And actually, if you see pictures of a reactor with a blue glow, that corresponds to Cherenkov light that is created by charged particles coming from radioactivity from a nuclear reactor. It's a blue and UV frequency light, typically. And so you can detect this light to see the presence of particles in the water. Now, there's one instance of this class, a famous one. This is called Supercommunicanda, and this is a 40, or it's actually total 50 kilotons of ultra pure water in a cylindrical detector that is underground. It's underground to keep away from cosmic rays in a mine in Japan. So it's 40 meters high and 17 meters radius. And the inner surface of the cylinder is covered with very sensitive light detectors called photomultiplier tubes. And this allows us to see the Cherenkov rings that come from particles, actually from lots of sources, but including supernova neutrino bursts. Here's a picture of what it looks inside Super K. If a supernova happens at the center of our galaxy, Super K will see 10,000 neutrinos from all within about 10 seconds. So it will be an enormous burst of neutrinos. The entire detector will light up with these the signals from these neutrinos. And here's a little simulation that my student did here. This is an image of what the detector looks. It's an unrolled view of the cylinder. So it's kind of a projection of the walls of the cylinder. And each dot is like a pixel from a light sensor. And when I click on here, what you're going to see is in real time what this will look like from a supernova. And you'll see these plots around will show how the signal is building up. Oops. Oops, that's not going. Let's try that again. Okay, there we go. Boom. So the thing over 10 seconds, you can see these rings projected on the side, and a whole bunch of them all within a very short period of time, within a few tenths of seconds. And what you can see here is you'll be able to tell from these neutrinos an excess of neutrinos pointing back to a certain direction. And so the reason for that is that some of those interactions, not all of them, but some of them result from neutrinos that are kicking atomic electrons, which are light. And so the neutrinos will kick them, and the electrons will recoil and they'll zoom off, but they will remember the direction they were kicked in. And so if you can, because they're light, they remember this very well. And you can infer from the distribution of them, you can see an excess that is in the direction the neutrinos are being kicked to, and you can actually figure out where the supernova is going to show up on the sky. So this is something that is really cool, that we really would be an amazing thing that a detector like Super K can do if there's a galactic supernova. Is you want to be able to tell the astronomers. Of course, the astronomers, if you say, hey, a supernova just happened, they want to know where, and they'll be upset if they really don't know where. They'll be a lot happier if you can tell them, look over there, and that will give them an idea of where to start looking. So the next generation detector is something called Hyper K, where it's something like it's actually going to be about 10 times the size of Super K, and this would have more than 100,000 neutrino interactions in about 10 seconds from the galactic center. So this is a next generation detector, which should be built at the end of this decade. There's another kind of water detector that you might have heard of, and this is a detector that is mostly looking at really high energy neutrinos. Actually thousands of times the energy of supernova neutrinos. And this is a kind of detector, it's actually built at the South Pole and it has these photosensors that are embedded in strings in the ice. And these are nominally for really high energy neutrinos, but what they could see if a supernova happens is the entire ice is going to glow with photons, and they can actually see this glow of photons and observe a supernova in this way. So this is actually a pretty cool complementary way of seeing a supernova burst of neutrinos in a neutrino detector, which is a kind of detector that was actually not designed to see really low energy neutrinos. It was designed to see high energy ones, and it's actually pretty cool that this detector can see a supernova burst. Scintillator detectors, I mentioned this is hydrocarbon, and it's a kind of material that will emit light when charged particles deposit energy in the material. And there's actually quite a lot of detectors that are made out of this kind of material that are typically around kiloton scale. Here's some pictures, icons showing them. So there's some in Italy. There's one called Snow Plus in Canada. There's a new one called Juno, is about 20 kilotons. It's being built in China right now. And so there's a lot of examples of these. And these will also have a very bright burst of neutrinos. They tend to have they're not very good at pointing, but tend to be able to measure with very good energy resolution the neutrinos that are interacting in it. Now, argon, this is actually the kind of detector that I'm personally working on most. And this is a kind of detector which is quite different from the other detectors which see light that's emitted, so either Cherenkov or scintillation light. These are detectors where instead you are able to measure the actual track of the charged particles that the neutrinos create. And so they're able to really, it's a kind of detector where you have an insulating material, it's liquid argon, a particle makes a little track of ionization. It basically kicks off the electrons from the atoms, and then you put a really high electric field and you drift that charge, and you get an image of the detector, and the time that it takes to drift the charge tells you a third dimension. So you get kind of a three-dimensional track. They're very fine-grained. You can get really exquisitely precise tracks in these kind of detectors. There's a whole bunch of them that have either have been deployed or being deployed now in the US. A really huge one called Dune, which will be 40 kilotons of liquid argon, it's kind of now the major flagship program in the US for neutrino physics. And actually the main program of this detector is not supernova neutrinos. Supernova neutrinos is one of the goals, but the main goal is actually to study neutrinos that are produced in a beam from Fermilab sent 800 miles underground to South Dakota. The detector is located in South Dakota. So the main physics of this detector is trying to understand the flavor change of the neutrinos as they fly. However, while it's doing this physics program, while we're trying to learn about the properties of neutrinos, if a supernova happens, which is not too unlikely over the few decades this detector will run, then we will expect something like 3,000 neutrinos all at once within tens of seconds from a Milky Way supernova in this detector. And this will be really amazing. So these kind of detectors here, you can get these very precise tracks. This is a high energy event, which is more like one you would get from a beam. You get the little tracks correspond to the charged particles that come out of the neutrino interaction. The kind of low energy supernova neutrinos you get lots of them. They're a little bit scrappier. They're like little stubs, so they're maybe 10 centimeter size, so you could hold them in your hand. and they're kind of scruffier, but they still have lots of information, and we can actually track them. And actually, we should also be able to use them to point back to the supernova, because you actually get this precise track, and you can tell where the neutrino came from in many cases. And actually, that's one of the particular things that I'm working on at the moment, is trying to figure out how to do that most effectively. So the future, big detectors that we hope are going to be online in the next decade or so. There's Hyper K, which is the much larger detector for Super K, with respect to Super K, but it's of the same kind as Super K. There's Juno, which is 20 kilotons of scintillator in China. And there's Dune, which is the liquid argon US-based flagship experiment. And my dream is for all of these detectors to be online when a supernova happens in the galaxy, because it would be tremendous information. These detectors are highly complementary. They really see different kinds of neutrinos. The water and scintillator detectors actually see electron antineutrinos, and argon sees electron neutrinos. And so they actually are seeing different parts of the signal. It's kind of like seeing different colors out of a spectrum. And so it's something where you really want all of these. These are not competing experiments. You want everything. You want all the flavors. You want the whole signal. The more the merrier. The more detectors that are online, the better the science that is going to come out. And so this is really something that's a worldwide collaborative effort is going to get the best science out. And speaking of that, I mean, the science of the signal is something that you can look at leisure after you've taken your data. If the burst happens, you record the data, you can look at it for as long as you like. But there's some urgency to the detection. You also want to be able to tell astronomers on a very short time scale, oh my God, better go look for something right now, because there could be information in the very early supernova observation that is a value that you will miss unless you look right away. And so for this reason, we have had, actually now it's getting close to 2 decades, we've had a system in place. It's called SNOOS, which stands for Supernova Early Warning System. And it is a global network of detectors that are sensitive to a supernova burst. And so I've mentioned some of these here. This is the original SNOOS, or the original planary SNOOS. This is as of, I think, about 4 or 5 years ago. Some of these detectors have now turned off. They finished their mission. But the canonical members here, we had, there's Super K. Camland is a scintillator detector, also in Japan, nearby Super K in the same mine. Diabe was an experiment in China. Borgsino and LVD are at Gran Sasso in Italy. LVD is still running. Borgsino is now turned off. HALO is a lead-based experiment in Canada, and IceCube is the detector at the South Pole that I mentioned. And so these were all members of this network, where the idea is that if any experiment sees a burst of neutrinos, it sends a message to a central computer, which looks to see if there's a coincidence. And requiring 2 bursts at the same time gives you a much higher confidence alert that something is up, that there's actually a supernova that has happened. And we have not had any. There have been no supernovae that we know of in the time that SNOOS has been online. But the idea is that we will be even more ready. There's actually an upgrade underway right now called SNOOS 2, which is a much, you can see from the graphic, it's a much slicker, fancier system. And we have a lot more functionality, better pointing, and lower latency, so faster alerts, and better information. So this is this SNOOS 1 is still running. SNOOS 2 will replace it in the near future when it is fully deployed. And just to point out here, the far side of the Milky Way is 650 light centuries away, and that means that 2,000 core collapses have actually happened already. Of course, it will take 650 light centuries for all the neutrinos from them to get to us, but they are coming. The neutrinos have already been emitted, and they are on their way to us. And we just have to hope that some of the neutrino wavefronts are going to intersect with our location in the galaxy sometime in the next few decades. It will be really super exciting. But the neutrinos are out there; they're coming. Let me just make one little note, since this has been in the news from time to time. You may have heard the Betelgeuse, which is a star you can see in the winter sky easily. It's the reddish star on the shoulder of Orion. it's been getting dimmer and brighter. It's been changing its luminosity, and some people have been thinking, is it going to blow up? This is actually a very nearby star. It's less than a kiloparsec away. It's something like I think 180 parsecs. So that's actually in our global neighborhood, really very close to us. It's a red giant, and it's a star that could blow up anytime. And the worry is, or both the hope and the worry, depending on your point of view, is that is this dimming and brightening of Betelgeuse, is that a sign that it's about to blow up? And the answer is probably not. The dimming and brightening, that's probably nothing to do with whether it's about to blow up. It could, however, blow up anytime in the next 100,000 years, which of course in astronomical timescale is very soon. But in fact, on our human timescale, it means that nothing may happen in our entire lifetimes. But if it does, we would see 25 million neutrinos in super K, which would be absolutely fantastic. It would be really amazing. And it could be tomorrow. And our goal as neutrino physicists is that we will be ready. We will be ready to swallow a signal of 25 million neutrinos and extract the most information from it. So here's the summary of how we can see neutrinos, how we can see explosions from underground. Is the next neutron star or black hole birth in the Milky Way will be heralded by this brilliant 10-second flash of neutrinos, and we are ready with these vast underground vats to see them. And in fact, you can sign up to be the first to know. You can sign up. The webpage for SNOOS is here, and you can join the mailing list. So you could actually, this is actually amateur, I didn't say this, but amateur astronomers are part of the community that's ready to go find that first supernova. And amateurs really know the sky very well. And it may be that among amateurs are the first people to see the first light from the supernova. And so here's a picture of Dorothy in black and white looking for the supernova. And the future will be a bigger and richer signal, more flavors. So it's kind of like more colors. And there's also gravitational waves. There's astronomy in different wavelengths, and messengers is coming more and more alive as the years go by. And the neutrinos are coming, and we will be ready. So I will stop there.
All right. Well, thank you so much, Kate. This was such a wonderful talk. Very pedagogical, very entertaining, very insightful, beautiful physics. Are there more questions? There were quite a few questions already, but if you have more questions, go ahead and type them in. I see there is a question from Gordon. Many and perhaps all core collapse supernovae are thought to produce relativistic beams or jets. Are the neutrinos also beamed, or are they emitted isotropically?
Oh, that's a great question. So some recent models do show anisotropies. The answer is mostly anisotropically. For the low energy neutrinos, they're mostly thermal, actually. But there are some models. There's one that's called LISA, LECA, where in fact, due to flavor effects, due to essentially oscillation effects, there could be some preferred directions for neutrinos, and there could be a flavor dependence of the neutrinos that are emitted in different directions. So it might not be completely true that they're isotropic. High energy neutrinos, the ones that are GeV energy, that are actually not coming from the core, that are actually coming from, for example, pions produced in actual jets, like the same kinds of jets that would produce gamma rays. Those are likely to be beamed, and actually those are the kind of neutrinos that are the target of detectors like IceCube. So they're looking at GeV, TeV scale neutrinos, and those are much more likely to be beamed. They're actually produced by the same kind of mechanisms as gamma rays. But the thermalish neutrinos that are coming from core collapse are quasi-isotropic, although there may be some directionality to it.
Catherine, if you have more questions, go ahead and type your next question, and we'll wait for that. While we're waiting for that, Kate, I had a question. So if we had a very powerful telescope or some sort of an array looking at a star that's perhaps about to explode, how much time advance warning could we see that there was going to be an explosion? So could we see like a few seconds before the explosion some dimming of the luminosity and then the explosion?
I think not. You mean optically,
Yeah,
or
yeah,
I
exactly.
think the answer is probably not much. I think for some classes of stars that are fairly naked, like Wolf-Rayet stars, that might not be quite true. There might be some possible pre-supernova activity. I think so. I'm not really the expert on the astronomy. I'm a neutrino person, but my understanding is that there are some classes of stars where you might get some pre-supernova burping or something, but most of the time, all of the all of the stuff is happening deep inside the star. Um, that said, in fact, there's possible neutrino signatures.
Okay.
There's what are called pre-supernova neutrinos that are change. So as the star comes into its very final stages of stellar evolution, it's burning heavier and heavier elements. And each of those subsequent stages, it's shorter and shorter. In fact, one expects a neutrino production from the fusion reactions to increase. So you actually do expect an
I see.
uptick in both
I see.
flux and also typically energy spectrum of the neutrinos that are coming out. Um, it could be days or up to hours before the actual collapse, depending on the type of progenitor. However, the flux of these is low enough that they're hard to see in a neutrino detector unless it's very close. That said, there are some models for which in the largest detectors that we foresee, such as Hyper-K, you could actually see a pre-supernova signal perhaps hours or days ahead of time, maybe out to the center of the galaxy.
I see.
So, so in the most optimistic assumptions, and actually that's one of the things that SNOOS 2 is going after, is to see if we can enhance a possible pre-supernova detection. So that's like a real early warning, which would actually be extremely, it would be amazing
Yeah, yeah.
if we could do
Tremendous.
that.
Okay, Catherine has written, my understanding is that neutrino oscillations are connected to the fact that the different neutrinos have different masses. So they are not energy eigenstates, but they are flavor eigenstates. Is there any property analogous to flavor that distinguishes electrons, muons, and tau particles?
I think those particles are in fact flavor eigenstates. I mean, in well, I mean, it depends. The state that participates in the interaction is a flavor eigenstate.
That's right.
So, it's the same. It's the same property for the neutrinos and the charged leptons. They're either mass states or flavor states. But the reason you can get the oscillations with the neutrinos is that their mass differences are so small that it's within the smearing allowed by the uncertainty principle. So that's kind of
Yeah.
but that's not the case for charged leptons.
Yeah. Okay, we'll take one last question. I was also wondering about the 10-second time scale for the collapse of a supernova. With the back of the envelope calculation, looking at the radius of the sun versus the distance from the sun to the Earth, and using the idea that light takes 8 minutes to travel from the sun to the Earth, I came up with an estimate of 2.2 seconds at the speed of light for the sun to collapse. I understand that the sun will go nova rather than supernova. The supernova forming stars have larger radii, so altogether, I'm estimating that the collapse occurs with matter moving quite close to the speed of light, question mark?
I think that is true. The 10-second time scale, however, is and okay. So one thing, it's the collapse. The initial collapse is just the core of the star, which is typically something which is made of heavy elements, and it's much smaller than the entire star. Like Betelgeuse is this big, enormous, puffy thing with a radius, I think, maybe beyond the Earth radius, the Earth's distance from the sun. So it's this enormous thing. The actual action of the burning tends to be happening in something much smaller. And so that's the relevant distance scale for that collapse time scale. Yes, it does happen at very high speed. But the time scale for the neutrino emission is actually not the collapse time. It's the It's actually the diffusion time for the neutrinos to come out of the core. And so it's actually governed by the neutrino, the core is so dense that even neutrinos come out at less than the speed of light because they bump into things. And in fact, that interaction rate of the neutrinos is, that's what governs how long it takes the neutrinos to come out of the star. And it also affects the explosion as well. The neutrinos are interacting. They're so dense. The matter is so dense. The neutrino density is so high that the neutrino energy coupling with the material is actually sufficient to affect the collapse itself. And so the time scale for the neutrinos to actually break out is something like 10 or a few tenths of seconds.
Okay.
Whereas photons, it could be a day, right? It could be very long.
Yeah, mean-free path issues. Yeah.
Yep.
Yeah. Thanks so much, Kate. I think we'll stop it there. I'll stop the